Maybe the most important operation when we're working with matrices algebraically is to multiply two matrices together. That's called the product of the two matrices. For example, if I have matrices named A and B, then I might multiply them together and call the product AB, like this. The order is important. As we'll see later, AB does not mean the same thing that BA means. So let's say we're trying to compute AB, A times B, in that order. How do we get the entries of the product matrix? Well, in order to find the entry in a given position, let's call it the ith row and the jth column. For example, that might be the 4th row and 5th column. What we do is we take the ith row of the first matrix in our product. So that would be the ith row of A. And we take the jth column of B. And so each of those, that row of A and that column of B, we can think of as a list of numbers. Then we match together numbers from those lists. We can take the first number from each list and multiply those together. The second number from each list and multiply those together, and so on. And after we've done all those multiplications of individual numbers from each list, we just add the results. Now, this process only makes sense if we can match things up to multiply together. So as we were taking the list of numbers from a row of A and the list of numbers from the column of B, those lists have to have the same number of values in each of them. So how many numbers are there in a row of A? Well, that's just how many columns A has. And how many numbers are in a column of B? That's how many rows B has. So in order to calculate AB, A has to have as many columns as B has rows. We'll see that in some examples here. Let's say we have this A and this B, and we want to compute A times B. What do? Well, let's say we want to calculate the entry that would go right here. Where is that entry in the product? It's in its first row and its first column. So I take the first row of A and I take the first column of B. And I think of those as lists of numbers. So from A, I have the first number in the list is the number 1. And then from B, the first number in the list is the number 2. So I take those entries that match each other, the first number from each list, and I multiply them together. Similarly, I take the second number from each list and multiply those together. So that's 2 times 0. After I've computed all of those products of numbers, I just add the results. So 1 times 2 plus 2 times 0 should equal 2. And that's the entry that goes into the first row, first column of A times B. What if I want the number that's in this position? So that's in the first row, second column of the product. I want the first row of A and the second column of B. And I'll do the same procedure. I'll multiply this 1 times this 4. That gives me 4. This 2 times that 1 gives me a 2. So I had a 4 and a 2, which add together to give me 6. Let's look at the entry that goes right here. So that's now in the second row. So we want the second row of A. It's in the first column, so I want the first column of B. And if I take 3 times 2 plus 3 times 0, I get 6. Finally, for this entry, I want the second column of A, the second column of B. 3 times 4 is 12. 3 times 1 is 3. And if I add those results together, 12 plus 3 is 15. That's it. That's how we calculate a product, like A times B. Let's look at another example. This time A and B are different. A is a 2 by 2 matrix. B is a 2 by 1 matrix. So I'm going to be able to compute AB, but it's going to work out a little bit differently this time. So I start out, again, wanting to compute the entry that goes here. It's in the first row of the product, so I want the first row of A. It's in the first column of B, so I want the first column of B. And notice B only has one column. So when I compute 3 times 2 plus 1 times -1, that's 6 minus 1, which is 5. How about the value that goes here? Well, that's in the first row of A and the second column of B, but oh, wait a minute. B doesn't have a second column. So that means the product doesn't have a second column either. There is no entry right here. The product only has one column because B only has one column. Similarly, there would not be an entry down here because for that we would need the third row of A, and A doesn't have a third row. So the product has as many rows as A has and as many columns as B has. So that means we don't need to compute a second column, we just need the entry that goes in the first column, second row. And if you use the same procedure we've been doing, you'll get a 4 for that value. Let's try C times D. So this is an example with bigger matrices. So first of all, let's see if we can predict the size of the product matrix. So C has 3 rows, and it has 3 columns, so the dimension is 3 by 3. D has 3 rows, but it only has 2 columns, so the dimension is 3 by 2. Now, in order for the multiplications to make sense, C times D, we need the number of columns in C to match the number of rows in D, and it does. These inside numbers here, 3 and 3, match. That means we're allowed to multiply these matrices together. And then if we look at the numbers that are left over, those are going to tell us how many rows and columns the product has. So because the product has the same number of rows that C does, the product has 3 rows, and it has the same number of columns that D does, so it has 2 columns. CD will be 3 by 2. It's good to know that in advance so that we know which entries we need to compute. Now let's start doing that. This entry in the first row, first column, will come from the first row of C and the first column of D. So first I want 1 times 2, that's 2. 1 times 1, that's 1. 0 times -1, that's 0. And then I want to add all those results together for a total of 3. The next entry is in first row, second column. 1 times 1 is 1. 1 times 3 is 3. 0 times 0 is 0. And when I add these together, I get a total of 4. And then that's it. Remember, CD had 3 rows and 2 columns, so I don't have any more columns to compute. I can move on to the second row. And you can complete this the same way we've done before. So for example, the last entry here is in the third row, second column. So I want 1 times 1, 1 times 3, 2 times 0. I want to add those together. 2 times 0 is actually 0. I want to add those together, and the result is going to be 4. So we had C and D were 3 by 3 and 3 by 2. CD was also 3 by 2 because it has the same number of rows that C does and the same number of columns that D does. Let's use that idea to see if we can figure out the dimension from another product. So imagine I'm calculating A times B, where A is 5 by 4 and B is 4 by 7. and I want to know what will the dimension be of the result I get from computing A times B. Well, first of all, we want to make sure that the numbers on the inside of this expression match. The dimension of A, the dimension of B written in that order, since we're computing A times B, the 4's match. That means we're allowed to compute this product. And if we do, it will have the same number of rows that A has and the same number of columns that B has. So it'll have 5 rows and 7 columns. That means it's a 5 by 7 matrix. What if we try to compute the opposite order, B times A? So I'm putting B first. B is 4 by 7. And then A. A is 5 by 4. Now the first thing we would do is make sure that the multiplication is legal, but it's not, because these don't match. 7 and 5 are not equal. The number of columns for the first matrix is not equal to the number of rows in the second matrix. So this multiplication is not even legal. That means B times A does not exist. It is not defined.